Welcome to Chemistry with Dr. Z. In this video, I will be talking about chloroalkanes and chlorofluorocarbons. So let's start by talking about chloroalkane and how to form these compounds. So chloroalkanes can be formed from alkanes. Alkanes in general are fairly inert toward most reagents because they only contain covalent bond, single covalent bond between either carbon and carbon or between carbon and hydrogens. So they are non-polar bonds and they are not easy to break. So to form chloroalkanes from alkane, we use a reaction called radical chain reaction. Radical chain reaction is a photochemical reaction that forms alkanes from chlorine. The radical or the main catalyst for this reaction are the free radicals that are formed. And free radicals are basically particles which have unpaired electrons. So if we have a bond between two atoms, let's say between two chlorine, the homolytic fissure of the bond between the two chlorine leads that each chlorine atom will only take one electron of the two electrons that are shared for the covalent bond when the bond is broken. That will create two free radicals. Each free radical will have one unpaired electron. They don't have a positive or a negative charge, but they will have unpaired electrons. These free radicals are very reactive and they will initiate a radical chain reaction as we will see now. So how does this reaction proceed? The first step in the reaction is the initiation step. In the initiation step, we have the chlorine gas, which is subjected to UV light. UV light will initiate the homolytic fissure of the bond between the chlorine atom. That will lead to formation of the chlorine-free radical. Chlorine-free radical then will start a propagation step or will start the chain reaction. In the propagation step, the chlorine-free radical will react with methane, and that will give a free radical, methyl free radical, and hydrogen chloride. So the free radical react with methane, takes one hydrogen, and leaves a free radical of methyl. Then the methyl free radical again will react with chlorine, which already exists in the reaction mixture, and will give us again chlorine free radical and methyl chloride. The chlorine free radical will again react with methane to give more free radicals. So basically the propagation step is the step where more free radicals are being produced. So this is the propagation step. All the time there are more free radicals produced. And then the termination step is the last step of the reaction. And in termination step, the free radicals in the reaction mixture will start to react with each other to give neutral compounds. So the chlorine free radical react with the methyl free radical to give methyl chloride, or two methyl free radicals react together to give ethane, or the free radicals of chlorine react together to give chlorine. So then when all the free radicals finish, then the reaction will end. The nature of the final products for these reactions, the free radical reaction or the free radical chlorination of methane will depend on whether the chlorine or the methane are in excess. So if the chlorine in excess, the chlorine-free radical will attack methyl chloride that has been formed and will give us different alkyl halogenated alkanes. So we'll give dichloromethane, trichloromethane, and tetrachloromethane. But if methane is in excess, then the product will mostly be the chloromethane. Chlorofluorocarbons, they contain no hydrogen, so they are halogenated compounds which contain no hydrogens at all. They only contain halogens and carbon. Examples of these are the trichlorofluoromethane, which has 3 chlorine and 1 fluorine, and the trifluoromethane, which has 3 fluorine and 1 chlorine. CFC has a problem and it can affect the ozone layer. So let's first talk about the ozone layer. So ozone present in the upper atmosphere and naturally in the atmosphere, the upper atmosphere, and it acts as a chemical screen. The ozone layer or the ozone absorbs the UV radiation from the sun and prevent the UV radiation, too much of the UV radiation from reaching the earth. The problem with the UV radiation is that it can cause sunburns and skin cancer. So how is the ozone formed? The ozone is formed naturally in the upper atmosphere. So we have the oxygen in the atmosphere which absorbs the UV light and that will make the oxygen-free radicals. So oxygen-free radicals will be formed naturally in the upper atmosphere. And then the oxygen-free radicals will react with oxygen molecules to give the ozone molecules, and that forms the ozone layer. So how does CFC affect the ozone layer? CFC makes holes in the ozone layer. What happens is that chlorine-free radicals are formed in the upper atmosphere. Because of the chlorofluorocarbons that we use and they reach the upper atmosphere, they can absorb UV light and that will give free radicals. One of these is the chlorine-free radical. The chlorine-free radical then that has been formed will react with the ozone and will give oxygen and other free radicals. These free radicals will react even further with the ozone to give more oxygen and chlorine-free radicals. So the chlorine that has been reacted in the first step will then be regenerated in the second step. So chlorine here acts as a catalyst. So the overall reaction, we have three ozone molecules will give us two ozone molecules will give us three of the oxygen molecule, and the chlorine-free radicals will be the catalyst for this reaction. This is how CFCs or chlorofluorocarbons will destroy or will make holes in the ozone layer. So CFCs are now banned. So let's first talk about CFC and why they have been used. So CFCs are unreactive, they are non-flammable, and they are non-toxic. So normally we would think that it's good to use CFCs, and they were used as coolant gas in fridges, as solvents, and as propellants in aerosols. However, the CFC causes damage on the ozone layer, so the advantages of using CFC didn't outweigh the danger it causes or the damages it causes to the environment. This is why CFCs have been banned. However, scientists have found or developed some alternatives to CFCs which don't have any chlorine, because these ones will not form chlorine-free radicals, so they will not destroy the ozone layer. Examples of these are the hydrogen fluorocarbons and the hydrocarbons. These don't contain any chlorine, so they will not form chlorine-free radicals.